Hello students, good morning. In last class we have discussed vapor pressure, after that vapor pressure of liquid solution, and then finally we have discussed Raoult's law. Okay? So before going to today's class, just we'll take a revision of Raoult's law. And according to Raoult's law, we came to know that when there is a solution having two components, suppose A and B, and their mole fractions are XA and XB in the solution. Okay, and then suppose the partial vapor pressure of A is PA and partial vapor pressure of B is PB, and according to Raoult's law, the partial vapor pressure of a component is directly proportional to the mole fraction of the component in the solution. Okay, suppose we are considering A, so the partial vapor pressure of A is directly proportional to the mole fraction of A in the solution. This implies PA equal to, here we have to put a constant, and the constant is PA naught into XA, and PA naught is vapor pressure of pure liquid A. Okay, when B is absent in this case, then the vapor pressure of A will be PA naught. That means only A is present, only pure liquid A is present. Therefore, the vapor pressure of the component or of the liquid A is called PA naught, and it is always constant at a particular temperature. It is always constant, and so here we have put PA naught as constant. Okay, so it is the mathematical representation of Raoult's law. Okay, and we have already discussed in our previous class about Raoult's law. In today's class, at first we will discuss graphical representation of Raoult's law. So our heading is graphical representation of Raoult's law. In this graph, we will plot vapor pressure against mole fraction. Okay, and in the solution we have considered there are two components A and B, and their mole fractions are XA and XB, and we already know that when mole fractions are added, the result is always 1. Okay, suppose at this particular point the mole fraction of A is 1. Since the mole fraction of A is 1, therefore the mole fraction of B will become 0. Okay, suppose in this direction the mole fraction of A decreases, and at this particular point the mole fraction of A becomes 0. When mole fraction of A is 0, then mole fraction of B is equal to 1. Okay, and since at this particular point mole fraction of A is 1 and mole fraction of B is 0, hence only A is present. Okay, so at this particular point the vapor pressure of A is maximum, and according to Raoult's law, the vapor pressure is directly proportional to mole fraction. Hence, the mole fraction decreases, therefore the vapor pressure will also decrease. The vapor pressure will also decrease, and at this particular point the vapor pressure will become 0. Okay, and then At this particular point, the vapor pressure of B will 0 since mole fraction of B is 0. They both are directly proportional, and in this direction the mole fraction of A increases, therefore the vapor pressure will also increase. The vapor pressure will increase, and at this particular point the vapor pressure will become maximum, okay, and this portion will give the vapor pressure of pure liquid A, that is PA naught, and this portion will give the vapor pressure of pure liquid B, that is PB naught. We are considering PA naught and PB naught for pure liquid A and B, okay, and then when we connect these 2 points, then this straight line will give the total vapor pressure, that is PA plus PB, and according to Dalton's law of partial pressure, you already studied in class 11, the total pressure is always equal to sum of partial pressures, okay, and this straight line will give the partial vapor pressure of A, and this straight line will give the partial vapor pressure of component B, okay, and overall this graph represent the Raoult's law for the two components A and B, and in this graph we have plot vapor pressure against mole fraction, okay. So our next topic is ideal solution. Ideal solutions. So ideal solution is a solution which obeys Raoult's law over the entire range of concentration. Whatever the concentration is, these solutions will always obey Raoult's law, okay. So we can say that the solutions which obey Raoult's law over the entire range of concentration are known as ideal solutions. The solutions which obey Raoult's law over the entire range of concentration are known as ideal solutions, okay. And in case of ideal solutions, number 1, the volume of mixing is equal to 0. So that means when the solution is prepared by adding solute and solvent, there is no increase or decrease of volume. That means suppose we have prepared a solution having two components A and B, okay. The volume of A is suppose 5 liter and the volume of B is suppose 2 liter, okay. When we add them to prepare the solution, the resultant volume will always sum of these two volumes, that means 5 plus 2 liter equal to 7 liter. So in case of ideal solution, there is no increase or decrease in volume, okay. And next point is, in case of ideal solutions, the enthalpy of mixing is always equal to 0. That means in some solutions during their preparation, the process may be either exothermic or endothermic, but in case of ideal solution, there is no evolve of heat or absorption of heat, okay. So next point is, in case of ideal solutions, their enthalpy of mixing is always equal to 0, and In case of ideal solution, the most important point is the magnitude of solute then solvent and then solvent interactions are always equal. Okay, in case of ideal solution, the most important point is the magnitude of solute after the solvent and solvent interactions are always equal. Okay, before preparing the solution, in case of the solute interaction is present, and in case of the solvent interaction is present, and after preparing the solution, in case of the solution solvent interaction is present. Okay, and in case of ideal solution, the magnitude of solute after the solvent and solvent interactions are always equal. There is no difference between strength of these interactions. Okay, now our next topic is non-ideal solution. So we have discussed ideal solutions and then now non-ideal solutions. And non-ideal solutions are those solutions which do not obey Raoult's law over the entire range of concentration. Non-ideal solutions. Okay, so non-ideal solutions are those solutions which do not obey Raoult's law over the entire range of concentration. Whatever may be the concentration, these solutions will not obey Raoult's law. Okay, and in case of non-ideal solutions, the volume of mixing is not equal to 0. Okay, and the enthalpy of mixing is also not equal to 0. That means during the preparation of this solution, the volume will either increase or decrease. Okay, and during the preparation of the solution, heat either evolved or absorbed. Okay, that means the process may be either exothermic or endothermic. So in case of non-ideal solutions, the volume of mixing not equal to 0 and enthalpy of mixing not equal to 0. Okay, and these solutions will always show either higher vapor pressure than predicted by Raoult's law or lower vapor pressure than predicted by Raoult's law. So depending upon the nature of vapor pressure, they are showing these solutions are classified into two types. Number one, solutions showing positive deviations from Raoult's law. Deviations from Raoult's law. And in case of these solutions, the vapor pressure is higher than predicted by Raoult's law. Okay, in case of these solutions, the vapor pressure is always higher than predicted by Raoult's law. And in case of them, the volume of mixing is positive and enthalpy of mixing is also positive. Okay, in case of them, the volume of mixing is positive and the enthalpy of mixing is also positive. Okay, and in these solutions, the magnitude of solute and solvent interactions are higher than solvent interactions. Okay, in case of them, the magnitude of solute and solvent interactions are higher than solute-solvent interactions. So these are three characteristics of solutions showing positive deviations from Raoult's law. Okay, in case of them, the volume of mixing is positive, the enthalpy of mixing is positive. After that, in case of them, the magnitude of solute and solvent interactions are higher than solute-solvent interactions. Okay, there are some examples of solutions showing positive deviations from Raoult's law, and they are: number 1, benzene and acetone. A solutions having benzene and acetone as its component shows positive deviations from Raoult's law. Okay, and another example is ethanol and cyclohexane. A mixture of ethanol and cyclohexane will show positive deviations from Raoult's law. In exams, questions are asked, explain why a solution of benzene and acetone will show positive deviations from Raoult's law. So we have to answer that in a solution of benzene and acetone, the magnitude of solute and solvent interactions are stronger or higher than solute-solvent interactions. Okay, therefore this solution will show positive deviations from Raoult's law. Okay, next we will discuss about solutions showing negative deviations from Raoult's law. At first we have discussed about solutions showing positive deviations from Raoult's law. Now solutions showing negative deviations from Raoult's law. Okay, and in these solutions the vapor pressure is always lower than predicted by Raoult's law. In case of them, the vapor pressure is always lower than predicted by Raoult's law. Okay, and in case of these solutions, the volume of mixing is always negative and the enthalpy of mixing is also negative. That is, the process is exothermic. In previous case, the process was endothermic. That's why enthalpy of mixing was positive, and in this case the enthalpy of mixing is negative, therefore exothermic. Okay, and the most important point is that in case of these solutions, the magnitude of solute and solvent interactions are weaker than solute-solvent interactions. Okay, in case of these solutions, the magnitude of solute and solvent interactions are always weaker than solute-solvent interactions. Okay, and there are some solutions which show negative deviations from Raoult's law, and these solutions are solution of chloroform and benzene. Chloroform and benzene. Another example is solution of phenol and aniline. In exams, questions are also asked, explain why a solution of chloroform and benzene shows negative deviations from Raoult's law. So we have to answer that in case of this solution, the magnitude of solute and solvent interactions are weaker than solute-solvent interactions. Therefore, the solution of chloroform and benzene shows negative deviations from Raoult's law. Okay? So, in this class, we have learned about graphical representation of Raoult's law. Then we have learned about ideal solutions. Then we have learned about non-ideal solutions. In non-ideal solutions, we have learned about solutions showing positive deviation from Raoult's law, and then we have learned solutions showing negative deviation from Raoult's law. Okay? In next class, we will study about the graphical representation of positive deviation and negative deviation. After that, we will learn about azeotropic mixture and then vapor pressure of a solution having a non-volatile solute. Okay? Thank you.